Thank you, everybody, for being here in the last session and sticking it out with me. I'm hoping to make the next 15 minutes worth your while. I want to talk to you about our project called Paralegal, which is a static analysis tool for privacy bugs. The context is that companies, companies and developers have to comply with a number of privacy policies to safeguard their customers' data. Some of these are access control, encryption at rest, data deletion, purpose limitation. If they get it wrong and introduce bugs, this incurs rightfully a large cost to the company because they're hurting their consumers. I want to show you a concrete example on data deletion in a social media web application called Plume. So Plume lets their users create blogs and then post to those blogs. Because they wanted to comply with data deletion, they created an HTTP endpoint that the user can invoke, which fetches their posts from the database, deletes them, as well as the user's account information with a delete row helper function. Now, as the application evolves, the developers add more functionality, and they allow the users to comment on each other's posts. However, what they forget to do is to update this deletion endpoint to actually erase this data from the database. And funnily enough, not only is this a real bug, this actually happened twice in Plume, once for the comments, and then again when they started introducing media. And since this is so easy for developers to get wrong, they really need practical tools to help them find these kind of subtle semantic privacy bugs. Specifically tooling that supports the wide range of policies that apply to applications, tooling that is uninvasive, requiring no or very few code changes and does not impact the behavior of the application, other than fixing bugs, obviously. And tooling that supports the evolving applications as, because there's churn in the code base. And lastly, tooling that supports the needs of real-world applications, such as the size of their code bases and their dependencies, as well as the pervasive use of third-party libraries. So let's take a quick look at what kind of tooling developers have available today to find these sorts of bugs. So information flow control is a rich research field that touches on lots of privacy concerns. Unfortunately, it can't enforce all of these policies. So for example, data deletion is outside of the scope of IFC. In addition, IFC often introduces lots of code changes to be able to actually check these properties. The developers could instead use a specialized fuzzer or a bug finder. But the problem is that those tools also only focus on one single policy at a time, which means they need a different type of tool for every kind of policy they want to enforce. Instead, they could be using a tool that automatically adds runtime checks. But this adds overhead over the application. And even worse, if the check fails, what happens to the application? Does it just crash? So it introduces a lot of disruptive behavior. Where we get closer to our goal is with an approach called code query engines, such as CodeQL from GitHub. These tools turn your project source code into a database and then give you a generic query language that you can use to find problematic patterns in the code. This gives you a lot of power. You can check basically arbitrary policies against the code. And it's also non-invasive because it doesn't require changes to the code. However, it struggles with that third-party library support and also the robustness in the involving applications. And I'm going to show you exactly what I mean by that by taking a look at what a data deletion policy for our Plume example would look like. Now, the first thing, my laptop did a weird thing. There we go. Now, the first thing you'll notice here is that this is quite a lot of code, and it looks kind of complicated. So we're going to really need an expert in CodeQL to both write this policy and also audit this policy. And zooming in a little bit over here, we can see that it actually mentions names of functions and argument positions and all this small fry minutia of the application code directly. That means when the developer changes the name of the function, the position of the argument, the policy expert will have to come in and actually update the policy to fix this. And lastly, what this code doesn't even show you is that this only works because the CodeQL people wrote thousands of lines of modeling code for the standard library so that they can even check that because otherwise it's too difficult to analyze. Now, this is not a practical approach, and developers really need better tools that addresses these particular shortcomings. So we created a tool called Paralegal that helps developers find privacy bugs in their code bases and really tries hard to be practical. So it supports a wide range of policies. It imposes no changes to the code or application behavior. It targets Rust, a mainstream programming language, and it innovates in three key ways. So its policies are succinct and auditable, and they're also robust to the changes in the code base over time. And lastly, Paralegal comes with an automated approach to modeling libraries based on the Rust type system. There are some limitations I would like to mention. As a static analysis tool, Paralegal cannot reason about the concrete values in the program at runtime, and because its policy language is so expressive and it makes some use of approximation that we'll see later, it has to accept the possibility of false negatives and false positives. But it can still find real bugs in web applications, and I'm going to show you how. So when the Plume developers use Paralegal, or if they use Paralegal, they feed the policy and the application code to the tool, which then can detect that the comments are in fact not being deleted and issues an error message. The developers would then fix the code in response to this message, run Paralegal again, which now returns no error anymore. So Paralegal enables a cycle of constant automated feedback that can help developers find these issues early. Now, here's what I'm going to talk about in the rest of the talk, starting with how these policies are actually specified, then how do we achieve this robust connection to the code, how do we actually check those policies, how this whole approach scales to real applications, and finally, some evaluation results. So for policies, let us actually dig into how Paralegal, or how you would specify the data deletion policy for Plume in Paralegal. Now, this is not going to be a policy that checks data deletion completely comprehensively, but be a useful approximation that developers can use to find bugs. And this is what this looks like in Paralegal's actual policy language. So this policy states that for each of the data types that we store about the user, or that Plume stores about the user, there should be a source somewhere in the application that fetches all of those types, and then it should go to a delete query. This language is based on first-order logic, which makes it quite expressive. So there's a lot of different policies that can be encoded. It's formal and unambiguous, which means that the results that Paralegal delivers are predictable. And its syntax is inspired by the language and structure of legal documents to make it auditable to non-experts. Another important way that Paralegal makes it more auditable is by really focusing the policy on its core concern rather than the minutia of the implementation that it's checking. This, however, raises the question, how does this policy actually relate to concrete elements in the source code? So for example, how does it know that data type refers to posts and comments? And here, Paralegal comes up with a new abstraction called markers, which form the interface between policy and application source code. To the policy, markers are a vocabulary of semantically meaningful categories such as user data and deletes. Lightweight annotations that are placed directly in the source code then identify members of this category. They're placed on either types or function arguments. So in this case, both the post and comment type are a type of user data. These annotations are maintained directly by the developers because they are the ones who are most familiar with the code base. And so if you imagine the delete row ID argument being either renamed or moved, the developer has to update this annotation, but there's no actual policy changes needed. And by placing the annotations directly in the source code, Paralegal also puts them right in the line of sight of code review of the exact elements that they refer to. Now, with the markers and the policy in place, we can run Paralegal, and we actually get an error message for our Plume example. So this last line clearly identifies that the problem is the comment type that is not being deleted. And to understand how Paralegal can make this determination, I would like to draw your attention to the goes to operator in the last line of the policy. This clause is a statement about data flow dependencies in the program, so how two values in the program relate to each other. And I'm going to show you how Paralegal actually represents those dependencies to be able to check this policy. A standard way to represent dependencies in a program is through a program dependence graph, or PDG, where the nodes represent values, or the values of variables over time, and the edges represent the data and control flow dependencies between those values. So if we apply this concretely to our function over here, this has a PDG that looks roughly like this. Paralegal deviates from the standard PDG in one way, which is that it annotates the nodes with the markers that we talked about before, propagating those from the annotated source code elements into the graph. Now, the statement source goes to query then specifically refers to the pattern that you see highlighted now in the graph, including the path between those two marked nodes. And because the comment type also carries the user data marker, Paralegal expects to see a similar pattern repeated for that type. And when it doesn't find it, it returns the error message. Once the developer fixes the code, this pattern exists, Paralegal finds it, no more error message returned. Now, in real applications that are not just 4 lines of code, the PDGs get a lot bigger. And so it's a lot more expensive to check them. So I'm going to show you how Paralegal actually wrestles with those large PDGs. One way to deal with it is by just producing smaller PDGs. So what if we don't include all the code in the PDG? Paralegal draws a boundary around the parts of the code that are relevant to the policy. And it uses a cheap approximation for the rest. Now, how can Paralegal possibly identify the parts of the code that are relevant? This is where the markers come in again. And they tell us which of the nodes could possibly be relevant to the outcome of running or checking the policy. And so this allows Paralegal to cheaply approximate a large part of the program while still maintaining the same accuracy. So I'm going to show you now how Paralegal is able to perform this approximation on the granularity of functions by leveraging its target language, Rust. So if we imagine trying to approximate one of those functions, Paralegal needs to know the answer to 2 questions. One is, how does data actually flow through the function? And the second one is, what is the function's impact on what's called aliasing? So what data pointers might refer to? Now, traditionally, when you try to do this, it's very imprecise. Depending on whether you choose a conservative or a liberal approach, you either include way too many dependencies and the tool becomes essentially useless, or you miss crucial dependencies that are important to find bugs. Paralegal's key insight is to leverage Rust as the only mainstream programming language where both of these questions can be answered quite precisely using just the type signature. So let's take a look at how this exactly works. I'm going to show it to you on this first question on data flow and on the example of the delete row function, for which I have here filled in the actual types. So the conservative approximation of how data flows through the function is to assume that all of the references passed to this function could be modified by this function. However, in Rust, mutability is explicit and enforced with the mut keyword. So Paralegal can deduce from the type signature alone that while DB may be modified and needs to be considered an output of this function, table cannot. And so fewer dependency edges are being inserted into our PDG. Paralegal performs something very analogous to this that's slightly more complicated, and you can read about it in the paper, for the impact on aliasing. But the long and short of it is that, again, the type signature tells us exactly what can and cannot alias. With this approximation, Paralegal can perform its pruning. With this approximation, Paralegal can perform the pruning optimizations I showed you before. It could also use it to deal with closed source code or calls to the foreign function interface. And developers can also explicitly instruct Paralegal to use this approach on libraries that are otherwise difficult to analyze. There is an important limitation to this. Since Paralegal now trusts the information in the type signature, then if for some reason the behavior of the function diverges from that, the real behavior of the function is not what this type signature claims it is, Paralegal may miss some dependencies. This is rare in Rust, but there are some data structures such as interior mutability where this is the case. We implemented a prototype for this approach in Rust as a compiler plugin that operates on the mid-level intermediate representation. And we leverage insights from flow history for this approximation that I just showed you, and also for we use its alias analysis. So the last thing I want to show you is how well this actually works. And the first question you might have is, does Paralegal actually find any bugs? And for this, we looked at 8 different web applications and formalized 11 policies. These web applications cover a wide range of domains. So for example, Lemmy, which is a social media application, here Paralegal was able to find 2 new subtle privacy bugs. One where, or 2 new subtle bugs, one where users that had been banned from a community could still act in that community, and another where users could make changes to communities that had been marked for deletion. Paralegal further finds 5 known bugs, such as in Lemmy, as well as Atomic, which is a database application, and the 2 data deletion bugs from Plume that we showed before. For now, the 4 applications, we formalized policies that were mentioned in their documentation and made sure that Paralegal would catch errors we injected into the application. And for mCAPTCHA, a privacy-conscious capture service, Paralegal uncovered what looked to be a data deletion bug. But when we checked in with the developers, they told us this was intended behavior somehow. And in the process, however, found a closely related data integrity issue. So to summarize, Paralegal finds real bugs in realistic applications. The second thing that a developer wanting to use this tool might want to know is it actually fast enough to be practical? And for this, we ran all of the 8 applications and the 11 policies. We include all dependencies in the analysis except for the standard library. And this is what the results are. At most, Paralegal's analysis for this setup takes 88 seconds. And Lemmy is dominating here because its access control policy covers literally every endpoint, every part of the code in the application. And if you ran Paralegal in an incremental fashion, then it would only have to do 1 endpoint at a time, which takes at most 3 seconds. So to conclude, when we include all dependencies in our analysis, Paralegal is fast enough to be run frequently, so for instance, as a continuous integration job. And the last evaluation question I want to answer here is, how well does it compare to the related work we saw before? So we looked at, when Paralegal runs this analysis over all the dependencies, it has to analyze quite a lot of code. So our optimization that we saw before really comes in handy here. So for 2 applications, Lemmy and Plume, this optimization is actually necessary, otherwise it runs out of memory and crashes. And for all other applications, it makes the analysis runtime about 35% slower, and the larger the app is, the larger the savings. Okay, so now the last question I want to answer is, how does it compare to related work? The long and short of it is, it can express more than IFC, and it finds more bugs than CodeQL does. And in the paper, we answer we also talk about how markers are robust and how Paralegal can be used interactively. So to conclude, I've introduced you Paralegal, a bug finder for privacy bugs with an auditable, flexible policy language that is robust to changing code bases, scales to real apps, and uses automated modeling for libraries. And it's open source and available. I would like to thank my excellent co-authors. Some of us are here, find us around the room. Thank you.